Hello everyone, welcome back. In this video, we're going to talk about theorem 1.42 in Watkins. You can find this theorem in other linear algebra books as well. It says, if the matrix A is positive definite, then A is non-singular. This can be proved using contraposition, which is how I'm going to prove it. So we're going to assume, right, the negation of this part here. We're going to negate this, and we're going to show the negation of this part. That's a contraposition proof. So we're going to assume that A is singular, right? So the opposite of this. So A is singular. We're going to show that A then is therefore not positive definite, right? That's our goal, to show that it's not positive definite. So let's start off our proof by assuming that A is singular. Let's see. So let A be a singular matrix, or just be singular. Then by definition, there exists, right? There exists, a non-zero y vector such that A times y will give you 0. Remember, if a matrix is non-singular, then the only way that A times y is 0 is if y is 0. But here we're assuming that A is singular. So when we say A is singular, we're saying that there is another vector, not necessarily 0, that will give you the opposite, that will give you 0. So here y doesn't have to be 0. That's the definition of singular. In non-singular, y has to be 0. So we're saying y is non-zero. That's very important, the fact that y is non-zero. Now, once we have that, we can go ahead and multiply both sides by the transpose of y. So y transpose times A times y will give you 0. Well, actually, will give you the y transpose times 0. But the right-hand side just goes to 0. Thus, we're left with just y transpose AY equals 0. Now, we got to compare this to the definition of positive definite. If we look at the definition of positive definite, the definition says that for any so positive definite says that for any non-zero vector, so in this case you can say x or y, so for any non-zero vector, we have the following property: x transpose, where x is the vector, A is your matrix, and then we have x, the same vector, non-transpose, and that has to be strictly greater than 0. If you have that for any non-zero vector, then it is positive definite. But if we look closely on the left side, we can see that we do have that, right? A times a vector and its transpose, but it's equal to 0. So that means that it is not positive definite. Because to be positive definite, you have to be strictly greater than 0. So we have proven that if A is singular, then it is not positive definite. Therefore, the opposite is true. If A is positive definite, then A is non-singular. By contraposition, if A is positive definite, then A is non-singular. Write a little bit better. Then A is non-singular. And if you found that helpful, please make sure to like the video or subscribe, and I'll see you next time.